Let's talk about simple harmonic motion. Simple harmonic motion is the one-dimensional projection of uniform circular motion. Pinocchio is traveling in a circle. His shadow, however, is traveling periodically, and it's undergoing a special kind of motion, simple harmonic motion. And what I'm going to do is I'm going to plot the position of Pinocchio as a function of time. We're going to make the story start here. This is going to be called the 0 meter position. So starting here, Pinocchio is at maximum position, and it's directed to the right of the 0 meter position, or whatever unit you might want to use. It could be centimeters or feet or miles. So at time 0, maximum position. When Pinocchio is here, he's a quarter of the way through the story. When Pinocchio's shadow is here, he's halfway through the story. Maximum position in the negative direction, to the left of the 0 meter, or equilibrium position. When Pinocchio is here, he's 3/4 of the way, and at 0 meter position. And when Pinocchio is back at the start, he's at the end of the story, and he's at maximum position in the positive direction. If we draw a best fit, we get a sine curve. More specifically, it's a cosine curve. Now let's take a look at the velocity of Pinocchio's shadow. That is the velocity of an object in simple harmonic motion. You'll notice that I have Pinocchio's nose pointed tangent to the circular path. That's representing the velocity when an object is traveling in circular motion. The shadow of the nose is showing the velocity in simple harmonic motion. You notice at the beginning of the story, there's 0 velocity. A quarter of the way through the story, you notice we have a maximum velocity directed to the left, so it's negative. Halfway through the story, we have 0 velocity. 3/4 of the way through the story, we have a maximum velocity in the positive direction. And at the end of the story, we have 0 velocity. If we draw a best fit curve, we get another sine curve. More specifically, a negative sine curve. Now, we could have created this graph by simply taking slopes. Okay, at the beginning of the story here, the curve has a 0 slope. Recall that the slope of a position time curve gives us the velocity, so we have a 0 velocity. Here we have a maximum slope, so we would expect a maximum velocity in the negative direction, since it's a negative slope, and so on. We can create the acceleration versus time graph using the method we used to get this one and this one, or we could just take the slope of the velocity time graph to create this one. But let's use the shadow technique. So what I need to do is I need to point Pinocchio's nose inward, because that's which way the acceleration is directed for uniform circular motion. So we can see at the beginning of the story, Pinocchio has a maximum acceleration to the left. So in other words, a negative acceleration. At a quarter of the way through the story, he has 0 acceleration. Halfway through the story, Pinocchio has a maximum acceleration to the right. 3/4 of the way through the story, the acceleration is 0. And at the end of the story, we have a maximum acceleration in the negative direction. And again, if we draw a best fit curve, we get another sine curve. More specifically, we get a negative cosine curve. Suppose we now plotted acceleration versus position. You see that we would get a linear relationship crossing through the origin like that. Because notice that when the position is a maximum and positive, the acceleration is a maximum and negative. When the position is 0, the acceleration is 0. When the position is a maximum and negative, the acceleration is a maximum and positive. From Newton's second law, acceleration is equal to net force over mass. So we could also create the same graph if we make this net force versus position. So this shows a proportionality between net force and position, where the net force is directly proportional to the negative of the position, just like the acceleration was directly proportional to the negative of the position. To make this an equal sign, an equality, we introduce a constant. So we get that the net force is equal to negative kx. This relationship is known as Hooke's law. K represents the force constant or spring constant, and it characterizes the elasticity of the spring.